Hello and welcome to ITech Labs. My name is Tan Gilinji. I'll take you through the RSA encryption algorithm, and I hope you have been able to preview some of our previous videos that I posted in regards to cryptography, especially on hybrid crypto systems and OSI security model. I think those will be fundamental videos that you need to preview before you listen to this video, that be able to take you through the process of generating RSA key pairs, that is a private key and public key, and some sample examples on how it is used to generate the key. So RSA is a part of a PKC algorithm, and we say that PKC algorithm uses a different key to encrypt and a different key to decrypt. So RSA algorithm was invented by Rive Shamir and Ademan as the basis of the crypto system. So it makes use of two keys, that is a public key, also known as asymmetric. So those two keys are different, but they're mathematically related. So the two keys are the public key that is shared with everyone, whereas we have another key that is referred to as a private key. So that key is only used to by the receiver or the sender information to decrypt the message or to sign the message that they are sending, whereas the public key is used to encrypt the message and also to verify the signature. So the RSA, the algorithm derives its security from difficulty factoring large integers. So that's a product of two large prime numbers. So the sender and the receiver, the system, they agree on the two prime numbers. So those numbers are multiplied to get a prime factor. So the larger the prime numbers, the more difficult it becomes for someone to determine the keys. So the keys here shows that you're using the public key to encrypt, and here you're using the private key to decrypt. So once you do the encryption, this is what we refer to as now the ciphertext, something that is not readily intelligible. It could be a digital envelope, but the receiver is going to get a digital envelope, subject it to their own private key, and then they're able to read what is the message that is in that digital envelope. So this is a model now. So I think you look at this, some of few mass aspect of factoring those numbers. In this case, we are saying that RS want to send an encrypted message to Bob, but RS requires to encrypt that message using Bob's public key, and then Bob requires to decrypt that message using his own private key, Bob's private key, and that's why we look at these generations of these keys. So what algorithm does is that RS generates her RSA key pairs. So they select two prime numbers. For instance, they can select, these are low numbers, but for the sake of explanation, we use so 11, any prime number, so of a certain range. So they can select two prime numbers, 11 and 13. So they assign values. So P is equal to 11, Q is equal to 13. So this is the modulus of it. The multiplication of these two prime numbers create what we refer to as an n, and that will refer to as a prime factor. What we say is that the larger the prime numbers, the more larger the prime factor that you have, then the more difficult it is for someone to reverse back to be able to know which numbers you multiplied to get that prime factor. The second step is that they calculate the taught. So a taught is a value that is generated from this equation here. The selected prime number minus 1. So if you had 11 here, it will be 11 minus 1, which is 10, and 13 minus 1, which is 12. We create a taught of 120. Yeah, so that is a taught. The next step for this RSA algorithm is that the person who is encrypting the message need to use the other person's public key, but who will be able to know that public key, how it is shared. So the selection of the public key is done using this formula. We are saying the GCD, the greatest common divisor of the taught, and the key that you select, the greatest common divisor should be 1. So it should only be 1. But we're also saying there's a condition here. We are saying that the key that you select should always be greater than 1 and less than the taught. So it means that in our case scenario, so it means that the key that can be able to be used to encryption is between 1 and 120. So it means that the larger the prime numbers, it means that you have a wider range of keys that you can use to select. But you can see here we are saying that the GCD that you use to select can already be one, should already be one. For instance, we can't select 2 to encrypt because 2 they share common devices with 120, which is a totient. So if you look at the 120, the devices of 1, 2 are 1 and 2. The devices of 120, you have 1, you can be divisible by 2, it's divisible by 3, it's divisible by 4, it's divisible by 5, it's divisible by 10. So you cannot use those because they share more than 1 devices. But you can use, for instance, you can't use 2, you can use 3, you can use 5, you can use 7, because so you can use 7 to encrypt because the devices of 7 are 1 and 7. And the only device they share between 120 is only 1. So you can use 7. At the same time, you can use 11. You can use 13. So it means that every time you're sending a message, the system actually select any of those possible keys that can be used to encrypt the message. So for instance, here let's choose 7 as a key that we choose based on the condition that the GCD of it, the devices of 7 are 1 and 7. And the only number they share with 120 or totient is 1. So it means that it satisfies the condition. So on the other side, Bob chooses to use key 7 and share it with Aris. So Aris and Bob can now select 2, 3, 5. They share more than 1 device, so they cannot select those because they share more than 1 device. I think we have said that. But the decryption process, it means that if the message will be encrypted using Bob's public key 7, then how will Bob be able to decrypt that message? Because that is a public key that was used. This is a Bob public key, which is 7 now. But how will Bob be able to derive this private key to decrypt the message? So the equation is done using this formula here. We say that Bob can create as private key here using what referred as Euclidean algorithm. And I'll try to summarize it here. We are saying that ED, and that is the key that was used to and selected, that is 7, D minus 1 divided by the totient, should give you an integer, a whole number. That's which give you a whole number. So you try to do substitution, and you substitute, you put 7D here, minus 1 divided by 120 should give you an integer. So you test using the values. So because you have 2 unknowns, the integer is unknown and the d is unknown. So to solve this equation, it means that you need to substitute the integer with a possible value. So the system provides those possible values and does a test until it arrives to an integer. So what will happen here is that now the encryption process makes use of our test. So for instance, if it's an integer 1, so it will be 7D minus 1 divided by the totient. Yeah, so keep on doing that. So you do the equation and you test the equation. So you go to the next value. Will it give you a whole number? So you give you a whole number, then that's the correct key of decryption. So for instance here, if the integer is 6, then you're actually saying is 120 times 6. Yeah, 120 times 6. The value you get, you take 1 on the other side, you say plus 1, then divided by 7. So you're able to derive what we refer to as 103 as a key to decrypting that message. So you have to do substitution, putting this value 7D minus 1 divided by 20, then you replace these values. Is it 1, is it 2, is it 3, until you get the value. If it is 6, then you're saying that you're doing cross multiplications, 120 times 6. Then negative goes to the other side, become a positive, you add it, then you divide it by 7 to return the value for D. So long as it gives you a positive number, then it actually means that that key can be used to decrypt that message. So this is a continuation of it. So in the encryption process, we assume the message, so the key pairs are generated. We have the value for, if from the previous slide, we say that the value for P and Q is 143. The value for E is 7, and the value for D we have found to be 103. So it means that our public key pair, take this, is 7 and 143. So in the encryption process, we make use of what we refer to as modular exponential. When you raise something to power of something, mod n, you actually generate a ciphertext. And the reverse of it is a decryption process. So in the encryption process, we get the message, you raise this to power E, the key that we used to encrypt, we selected that was key number 7, mode N. So N is a product of P and Q, which is 11 and 13 to get 143. So if you raise 9 to power 7 using your calculator, you should be able to get value, then mode 143, so it creates a ciphertext to be 48. So when Bob received this message, and this is a ciphertext, so Bob will get the ciphertext, raise it to the power of the decryption key, which is regenerated as 103, mode N, Bob will be able to generate the same key, which is 9. So in our example here, we are simulating that our message is 9. And you can try that and you can be able to see that if you raise that value to the power of 7, mode 143, you get a ciphertext of 48. And that ciphertext is decrypted by the receiver, which is now Bob. So the Bob is going to derive the key D, which is 103, get the ciphertext, raise this to power D, and then mode N to get what we refer to as 143, mode 143 to get back the message is 9. And that's how it is, because that's generation on the session key. And we use that as a way of showing that you cannot deny having sent the message, because the message was actually encrypted using the receiver's public key. So you cannot deny having not known them. So the other side, the person decrypting the message cannot deny having decrypted the message, because they actually derived the private key to decrypt the message, not unless they lost the private key to decrypt the message. So that's it about RSA. But then why the RSA algorithm? So it's become one of the most widely used asymmetric algorithm to provide a method for ensuring confidentiality and non-repetitions. Many protocols, including Secure Share, OpenPGP, SMIME, which are used for email security, SSL certificates, they all depend on RSA. But they make use of combinations of RSA using digital signatures. And some of the popular RSA libraries that you don't have that make use of these are OpenSSL, Bouncy Castle, Crypto, PY Crypto, among others. These are libraries that have these algorithms. So as a programmer, and you'll be able to see in our next labs, you'll be able now to use them and import them and be able to encrypt a file or a message using an RSA algorithm. Thank you. That's a brief overview of RSA algorithm. I hope you'll be able to do the computations. If not, then you'll be able to do as a message. You can be able to review and provide more labs that will help you to understand it better, but we'll be able to show you some practical applications of an RSA algorithm. Thank you for listening and also for subscribing to our channel.